afternoon and welcome everyone. My name is Sierra Lamonaco and I am the Alumni Relations Officer with the Faculty of Applied Science and Engineering, as well as the program lead for the School Lunch and Learn. First and foremost, I want to wish everyone in the audience a happy new year and thank you all for joining us here today for our very first School Lunch and Learn presentation of 2023. With alumni joining in and tuning in from all over the world, we are having alumni and guests joining us from 6 different countries today: Argentina, Canada, Singapore, Switzerland, Thailand, and the United States. Now, before we start today's presentation, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this place is still home to many Indigenous peoples from across Turtle Island, and we are so grateful to have this opportunity to work on this land. Now, I hope each and every one of you are excited for today's presentation because our guest speaker is someone who is dedicated to performing leading edge research with the goal of addressing challenges in the construction industry. Professor Daeho Kim's research on fostering a new and safe workplace that specializes in co-robotic construction is an excellent example of how U of T, through Defy Gravity's campaign, aims to power innovation to address industry challenges at the intersection of diverse disciplines. Now, a quick housekeeping item. At the end of today's presentation, we will have time for a formal Q&A. Should you have any questions for our professor, please submit them using the Q&A button at the bottom of your screen. For the individuals who submitted their questions during registration, thank you for pursuing your curiosities and sharing your insightful questions with us, which we passed on to our professor. Now, without further ado, it brings me great pleasure to introduce the one and only, our MC and chair of the School Lunch and Learn program, my favorite person, Laurie Hevola. Laurie not only is an Electrical 65 graduate, but he's also one of the most dedicated and engaged members of our alumni community. Laurie has been the chair of the School Lunch and Learn program for over 10 years and continues to generously dedicate his time to maintaining our long-established traditions. And with that, please join me in welcoming Laurie Hevola, who will now introduce our speaker for today's event. Thank you.
Thank you, Sierra, for your very kind introduction. And again, if it's not too late, a very happy new year to everyone that is able to join us today online. It is now my pleasure to welcome our guest speaker, Professor Daeho Kim. Dr. Kim is a professor appointed by the Civil and Mineral Engineering Department here at the University of Toronto. His research focus is to widen the horizon in construction by realizing the true value of co-robotic construction. His goal as a researcher is to lay a solid foundation for human-robot collaboration by establishing safe and cohesive teaming among workers and robots and reconfiguring the existing labor-intensive construction mechanism. Professor Kim's 4 research agendas are searching for answers to the following questions: how to ensure workers' safety alongside robots of varying autonomy, how to improve workers' physical, cognitive, and emotional comforts alongside robots, thereby having more productive and cohesive teaming between them, what the ideal work environment would be, not for human or robot, but for a human-robot crew, and lastly, how to foster a new workforce specialized in robotic collaboration. And now, without further ado, please join me in welcoming Professor Daeho Kim, who, by the way, is in Korea in person.
Thank you. As you saw in the previous video, our construction industry is more than eager to embrace the new robots to reap the benefit of improved productivity, profitability, and also workers' ergonomics. And we are now looking at an unprecedented chance to reform our labor-intensive construction into more automated and digitized construction with construction robots. And the robotic automation and digitization is a must for the Canadian construction industry that has suffered from a stagnant productivity and also poor safety. And good afternoon, ladies and gentlemen, and most welcome to a Civil and Mineral Engineering Department at the University of Toronto. This is Dr. Daeho Kim, an assistant professor at the Civil and Mineral Engineering Department. And it is my great pleasure to present you on my team's research aiming to realize the co-robotic construction in near future. That said, let's have a look at what is happening in our construction industry first. Let's jump in. The construction industry in Canada and internationally is actively gearing up to embrace a robotic solution. And here is what I found. The equipment manufacturers have retrofitted their equipment with the autonomous kits, and the robotics company are releasing a variety of construction robots at varying degrees of autonomy. And swimming with such tide, construction academia is exploring the new forms of robotic solutions. And however, at the effective point of view, there is a pressing challenge in deploying robots in unstructured and dynamic construction site. And simply to put, we are not ready to deploy such robots in our construction site yet. And today, I would like to draw your attention to a critical element in realizing the co-robotic construction, which is the worker's safety. The construction takes place in an unstructured and dynamic workspace. The layout and movements of entities are bound to be erratic as ever, and the field workers often fall into proximity to the motorized resources, exposed to the risk of forcible collision. And the number of fatalities due to the forcible collision is the direct evidence of the magnitude of such hazards. And it accounts for about 41% of the total construction fatality globally. The main point here is that the field workers are likely to be assuming a greater risk of accident in the co-robotic construction, where various types of mobile robots work alongside them. Take, for example, the also moving robots such as autonomous wheel loader, or take another, the collaborative robots such as humanoid robot being right next to the workers, and their laws and boundaries will overlap with the field workers at times, which would raise the likelihood of accident occurrence. For sure, the robots have various sensors and safety functions such as emergency stop. However, their intelligence and situational awareness are bound to be limited. To make the long story short, even though the robot's built-in safety functionalities are significant, we cannot solely depend on them. Thus, a conclusive and more comprehensive hazard detection technology that can apply to any robot is needed. And let's take a look at how my research team has additional shield to prevent such accidents. In this slide, I would like to explain how we can actually detect the proximity between on-site workers on foot and then motorized resources, including the existing equipment such as excavator or wheel loader, or excavator looking like robots. So in this research, actually our team fly the drone over the construction site, and then we develop artificial intelligence, which is a computer vision based, that can automatically detect the workers any type, any size. It doesn't matter female or male, and then it doesn't matter the clothing colors. The AI will detect the workers, will localize it on a pixel system, and also at the same time will detect the excavator or wheel loader, any other types of the construction equipment or construction robots which are mobile. And after we detect the entities of our target, such as workers and the motorized resources, and then the additional algorithm will measure the physical distance in a metric unit. For example, between the workers and excavator. Right now it's 5 meters or 7 meters or 9 meters. And by my publication already validated, the current accuracy about the proximity detection is more like a 90 or 90, early 90%. And in the metric error, it's about the 0.61 meters, which is quite promising. Let's take a look at some demonstration video. On here on the left top, it first detect the target, and then by using the reference object, we are going to need some rectification process so that we can eliminate any projective distortion, so that we can measure the physical distance between the two objects, even on the 2D image. Actually, the distance we are going to measure is a 3D distance, even on the 2D images. That's a new method that I developed. So this is how we can reuse a drone and the AI to identify the proximity hazard between the workers and the construction robots or other construction equipment. And further, what we can do more is about the proximity prediction. So let's say action can happen in any time, at anywhere. And it is called accident because we cannot expect. And then the simple idea was that why don't we predict the future location if it is possible? We can identify the proximity 5 seconds earlier so that we can give a feedback to the workers 5 seconds earlier. And at the same time, we can deliver a signal to the robot or equipment operators that the proximity that will happen in a 5 seconds future, so that we can give them a kind of a buffer time so that they can take an evasive action. It includes also to the robots. So how this prediction works, our research team also using a deep neural network, which is analyzing the individual trajectory patterns, and also at the same time, it learns the social pattern, social behavior between the multiple entities. So this DNN first observed like 3 seconds, and then based on the history of the trajectory, it will predict the future location of our target entities. In that way, we can get the future trajectory and also future proximity after 5 seconds. Right now, for sure, the trajectory prediction accuracy is a little bit lower than the proximity detection at the current frame. However, it still has a less than 1 meter error, which is still promising. And more promising fact is that the deep neural network and accuracy and speed is still evolving. Let's take a look at some demonstration video. See, first 3 seconds, it needs some observation time. And after that, it generates the future location. If you can see here, there is human workers as a person, and there's wheel loader and excavator. And the green, blue, and red line is a future location that this model actually predict. By this prediction, we can know the future proximity 5 seconds earlier so that we can give a more buffer to prevent the accident. These are just some examples of my research, how we can actually contribute to preventing the contact-driven hazard in the co-robotic construction. And also it can apply to the current construction setting where the equipment, mobile equipment and workers are working on the same site. And in this video, I also would like to introduce a very interesting research agenda here. As I show you the 2 videos, proximity detection and proximity prediction, most of my research relies on computer vision, the visual scene understanding, and also at back end, there is a deep neural network, which is we usually call artificial intelligence. And how we can train artificial intelligence, guys. Artificial intelligence is very similar with a human brain. The only difference between a DNN-based computer vision and human vision system is we have 2 eyes and also we have a brain. And then in the computer vision and then deep neural network-based computer vision, we are replaced that the human vision system with the two cameras, for example, replacing the two eyes, and also the supercomputer replacing the brain. And then we need to give a little bit more attention to the server side, the where the actual artificial intelligence model is stored. Here, the biggest challenge in construction robotics and also in the implementation and deployment is how we are going to ensure worker safety, and it depends on the accuracy and speed, and then speed of the artificial intelligence. And that also leads us to one more question: how we are going to train the artificial intelligence in a more accurate way. What we need to train are like human level intelligence. The one simple answer is we need the data. We need the training data. If you take a look at how Tesla's autopilot works, they actually collected and still in collecting a bunch of training data set. However, that does not apply to the construction setting well, because in the construction site, first of all, it is really hard to collect the videos at various viewpoints, and also it is hard to annotate the training data set. Collecting the videos or images is just a 10% of effort in preparing the training data set. The other 90% effort that we need to put is annotating our training images. Annotating means we are going to draw a bounding box, or we are going to annotate the human joint location. We need a number of annotations in one single image, and it takes a lot of times. So that was the first challenge in the construction industry. And then the second one, just simply to put, is costly and time consuming. For example, annotating the one image will cost around $10. And how many images we need? Nobody knows. We may need 1 million or tens of millions of training images to have a human level intelligence, or like Tesla level, the autopilot level, the accuracy. We need our construction specific training images with the annotation. But as I mentioned before, it is simply impossible with human efforts. May be possible, but it will require a lot of time and money. So I'm trying to get around this challenge by using the computer simulation and then the animation tool. What I'm working right now, I am creating the synthetic, the virtual construction scene by using the 3D background, the 3D point cloud, and also various of the construction motion data with the construction avatar having a various clothing setting. By combining the 3D background and construction avatar, construction motion, and also by modifying the camera viewpoint in the animation tool, I am actually generating a limitless number of construction training images. And also in my code, in our code, we are generating construction annotation automatically, because it was possible. We made it from the scratch. So in this research, actually, there is no single human effort required for the annotating the images. Let's take a look at how this simulation works. And then at the end of this video, you will see how the annotation will look like. See, we can change the viewpoint as we wish. So sometimes we may need a drone view, or sometimes we need a more close-up. And also there could be workers or multiple workers in like this. There is a 2D bounding boxes, or also there could be a 2D and 3D joint location. And here like a depth map could be annotated. And with these annotated data set, we can finally develop and train trustable and reliable artificial intelligence that can always detect construction workers or other objects of our interest. So here, this research is still ongoing, and the last step, by the way, I'm actually generating millions of training images to kickstart the training. However, someone may be curious about, is this synthetic images actually effective in developing a reliable artificial intelligence? Because obviously it is not real images. But I would like to let you know that for computers, the images is interpreted as a set of the numbers. So the computer take the images as a 3-channel of the numbers. So if we can characterize the scene characteristics in the simulation tool, then it actually doesn't matter for computer whether it is a real image or a synthetic image. There could be an effective training. And here is some interesting research outcome. If you take a look at the below, two examples here, if you can take a look at the original training images, it's just this figure called as a salience map. Let me just explain what it is. This salience map represents where this deep neural network AI model is actually attempt to make a decision. See, in the original training, the focus of the deep neural network is scattered, right? However, after we augmenting the training images, what we can see, the deep neural network focus is more attend to the excavator, which is our target to detect. So it is not just an example, it can happen in any other examples as well. So the data augmentation and data synthesization is absolutely one good research agenda that many other researchers are actually working on. These are about one research agenda about how we can actually train more accurate deep neural network artificial intelligence. This one is another interesting research topic. So what I'm doing in this research, even though we develop the artificial intelligence, but there is it's really difficult to actually demonstrate our artificial intelligence to the real construction robots. For example, let's imagine there is an excavator robot, real scale, on the construction site. And then due to the safety concern, we cannot just run the demonstration with the artificial intelligence because there are so many uncertainties. So I somehow try to come up with if there is any other measures that we can demonstrate and or try on our developed AI in a miniature scale construction robots. And however, there was no type of a miniature scale construction robot that we can purchase, or if we are going to prototype it, it will require a lot of research effort and research funds. So this one is quite interesting because I'm using a miniature radio-controlled excavator toy. This is just an entertaining toy, how usually we control it with a control panel. However, what I have done is I a little bit modified these engineering features with the Bluetooth and Arduino so that I'm right now actually giving the commands to this excavator toy, not by the control panel, but by my laptop. And then also I give some pre-programmed motions to the excavator so that this excavator can actually demonstrate the artificial intelligence. It is some kind of a small scale robotized excavator toy, which is it can be seen as just a small scale robot that actually takes the commands from my laptop. Take a look at how it works. And then the other advantage of having this system is we can also use a small scale excavator to generate training images as well. Because it is a miniature scale. However, for the 2D images, anyway, there is no scale information. By modifying the viewpoint, it can be seen as a real scale excavator too. And because I actually give the commands and I know every single motion data stored back end, we can just simply get the 2D and 3D annotation for the excavator pose, which can be greatly used in training the pose estimation of the excavator model too. Sierra, would you mind share your screen? This is quite interesting research topic. Using this excavator, actually, I'm also generating a training images. We couldn't get the result yet, but yes, thank you. Let me share my screen back. I believe the robotic construction is no longer the distant future, guys. And robotics will make their way into a variety of construction jobs, and someday will become integral to construction. And what the construction, a co-robotic construction present to construction industry sounds very promising. And the future construction work with robots will be likely to have a completely different horizon. And please imagine a future blueprint of the construction site, a space where workers and robots and harmoniously coexist and work together. And most of physically demanding, highly repetitive, and unpleasant tasks would be taken over by the robot, while human workers would focus on the tasks that require the fine dexterity and improvised decision-making too. And it is certainly positive that the robotic change will have the construction be more productive and be more ergonomically safe. And additionally, as the major load of construction workers shift from bodily dominant tasks to more intellectual ones, I believe the construction workforce can be more attractive to the prospective workers from a wider range of demographics and thus be more inclusive. However, the reality again, at the effective point of view, we must be capable of ensuring worker safety in the first place before the consideration of embracing such robotic solutions. And today, I shared with you only a small portion of my research related to the worker safety, but of course, there are more to come. My long-term objective is to investigate what we need to prepare in advance to realize the robotic construction and how to make its value maximized. And there will be many research questions that we may need to pay attention to as our industry heavily relies on manual labor. For example, what would be the ideal work process and layout for human level crew? And how can we foster the robot collaboration specialized workforce? And how can we retain the existing workers? And how can we make the inflow of the new workforce? Or which type of the new job will be created? Can we apply the existing industrial standard and regulation for robotics? We don't know yet. And many more questions will come. There will be plenty of unknown areas we need to explore, which makes me more excited. And this is it. It was my honor to share my research and vision with you. Thank you all for listening.
Thank you, Professor Kim. We will begin with questions. There are 2 questions online. The first is, how do you model the human motions for the simulated data, specifically to match realistic motions?
Thank you, Rory. That's actually quite a good question. First of all, it is not possible that we fully simulate the construction motions. Rather than that, what we are doing is we are using actually sensors. Sensor means we are using the wearable suit, and then we mimic the construction motion in the lab setting so that we just collect the motion data from the IMU wearable suit, or it could be also collected by the other vision-based motion capture sensors, for example, including the Vicon or OptiTrack. So for the motions, it is not simulated. It's a target to collect. That is a minor effort that we need to put. It is all about to get the more realistic motions in the simulation data set.
Thank you. The next question, what does the video capture of small-scale toy models, such as you showed, add that is seen with 3D digital model does not?
So here's the point. I'm working with synthetic data generation, and at the same time, the miniature scale, the equipment worker data, equipment data generation too. And the background was that we can also simulate, we can also synthesize a virtual construction scene with the virtual construction equipment. However, by reported many previous research, the synthetic data set, it is effective. However, it is not optimal. Somehow we need a real data set to fine tune our artificial intelligence at the end so that this model can actually work well in the real setting as well. That means we need both synthetic data set for the pre-training, and also we need the real data set for the fine tuning. The problem for the equipment data set, there is no way that we can collect. There is no way that we can annotate the 3D joint location of the excavator, for example. We cannot use a barcode, or we cannot use the OptiTrack. We cannot use the other motion capture system on the real scale construction equipment. That's the truth. That's just a fact. There is at a current status, we cannot. That's why I'm exploring the potential of the miniature scale excavator, because if we use a miniature scale excavator, we can actually can capture by modifying the viewpoint and the scale and the distance between the camera and the miniature scale toy. We can get it as a real scale excavator, but at the same time, we will get the annotation free because we are giving a comment.
The next question, do you consider the use of thermal imagery as well, such as infrared?
Amazing question. The infrared images, it also can be used in DNN training. And the major trend is that usually in the DNN training for the computer vision, the artificial intelligence, we are taking RGB image. RGB image literally has 3 channels, red value, green value, and blue value in a 2D camera coordinate system. However, this RGB image has some limitation. It only gives us the color value, color distribution. However, let's say, what if it is a nighttime? Because in the co-robotic construction, we may expect the robots can work during the night. And maybe there will be a couple of workers who manage or guide that the autonomous construction robots. Then how we are going to detect the robots in the night? Because the computer vision will rely on the light. We need a vision, we need the light. But if it is a nighttime, if the RGB value is not effective in identifying any scene, then that's where we can use the thermal images. What we can do is we are going to add RGB image plus the thermal image as a fourth channel. And we are going to use the fourth channel input in training. So that's just my previous idea. We couldn't get it to the physical research yet, but it's in my research plan too. That was quite a great question. And also the other thing, we can also use a depth map. If we use another channel as a depth information, we can develop the neural network for the 3D detection. Because in the 2D image, obviously there is a scale missing, the depth information missing. So there is a little bit limitation in the 3D object detection or 3D pose estimation using only RGB image. But RGB plus depth image, it can also help us to get the 3D analysis, 3D bounding boxes or 3D joint location. Thank you.
Thank you. The next question. Often excavators and machine operators on construction sites take their direction from a foreman or other crew members to perform precise, highly skilled motion. Do you see a scope for training robotic excavators to respond to hand signals in the field for performing such motions?
Could you repeat one more time, Laurie? I'm sorry.
In real life, often excavators and machine operators on construction sites take their direction from a foreman or other crew members to perform precise, highly skilled motions. So do you see a scope for training robotic excavators to respond to hand signals in the field for performing such motions?
Yes, that's of course. There is another AI development research agenda, which is recognize a hand gesture. And then how it works is it actually recognizes hand gesture and the robot determine what to do. So basically hand gesture is another type of commands. However, the major trend of the equipment robotics in the construction domain, it is not going to happen in the hand gesture recognition. It's more like, for example, one of the major trend is a teleoperation, and then the other thing is a fully autonomous construction equipment. So that is something new to me.
Thank you. The next question is somewhat related to an earlier question.
Mm-hmm.
Do you know yet whether weather and to what extent your detection and prediction technique might be affected by local weather, such as rain, fog, etc.?
That's a good question. As I mentioned before, the computer vision relies on the pixel value RGB or depth or thermal camera. And then by the weather condition, the RGB value will be affected. Then how we are going to address that issue is actually in the simulation of the synthetic data generation. I and my research team actually changing the weather condition too. So if the training data includes such a severe weather condition, the diversity of the scene color variation, it won't be too much problematic. But absolutely, if the training data set does not include such a diversity of weather condition, that deep neural network will not work under the fog or the other lighting conditions. That's a really good question.
Thank you. Next question. Which construction jobs do you think will be replaced first or lend themselves best to the robot's ability and safety profile?
Bricklayer. My answer is a bricklayer. My answer might be wrong, but what is happening right now in the starting from the US, there is I would just say it is not a fully autonomous robot. It's more like a tool or equipment. There is a robot called semi-autonomous masonry robot. And how it works is basically the productivity is 50 times higher than a human. That robot is just take the brick and then apply the mortar and then place the brick and 50 times faster than the human brick layers, and then the accuracy is amazing. It's already validated, and many construction companies actually using that robot already. So I would say the brick laying or labor time, such kind of very highly repetitive, but does not require the task, does not require some improvised decision making will be replaced first, because for the construction robot application, still in the construction site, there are so many uncertainties, and many times it only relies on humans' discretion. We need still humans improvised decision making. So maybe what kind of the job will be replaced first, then I would say the task that does not require thinking. So bricklaying is a good example, or labor time.
Thank you. Next question is somewhat related. Do you see a point in time where the use of people will become redundant in the construction process using robotics, et cetera? This would then shift the entire question of worker safety.
Not at all. Not at all. The major trend that the research, the construction academia is looking at is we are not thinking the construction robots will replace the human workers. But at somehow what we are imagining is the human crew. For example, a team of the multiple construction workers, let's say it's a crew, is going to be replaced by a human robot crew. However, as I mentioned, as I highlighted before, in the construction side, in the construction process for the construction job, is some kind of a series of uncertain tasks, a series of decision making, which is not possible by artificial intelligence at this stage. So as the next blueprint of the construction would be the co-robotic construction where human and robot are co-working together. If someone asked me, would it be possible that the construction robot will replace totally the construction workers, then maybe that will not happen before at least several decades. I don't know. It is something that I cannot answer to. But that's certainly not the next step we are looking at.
Thank you. In your presentation, you talked about the use of various sensor technology. How much does GPS play the role in your research?
I'm not using the GPS in my research. I do more interested in the computer vision and the neural network. For sure, many construction robot prototype, they are still be equipped with a GPS or LiDAR or radar or sonar. Those are for the localization and the proximity detection. But the reason why I'm more focused on, more interested in computer vision and deep neural network-based artificial intelligence is the visual imagery data has a more innate, how can I say, more rich information. We can draw some semantic information from the image, and then the deep neural network architecture and the number of the training images, and also a computing power for the training and inference, all those three are improving so fast. That means the potential of the computer vision and AI is still evolving. So that's why I'm more interested in the visual or scene understanding rather than using a physical proximity sensor such as GPS or a LiDAR and so on. Thank you.
Next question. How would collision warnings be potentially transmitted and received to the workers?
So very basic idea is that, let's say a drone can take a look at the construction site of the bird view. It can address some limitation of the ground viewpoint of the robots or ground viewpoint of the equipment operators. For example, the biggest challenge of the visual scene understanding is occlusion. Let's say if there is a wall, then simply we do not know. There is no way that we see the behind the wall. However, if we use a drone, then we can get a bird view. So, and the bird view are going to be shared to the equipment operator and the robot or the also workers. The basic idea is between the data transmission between the drone and the robot is by the wireless connection is possible, and how we can give a feedback to the workers via wearable devices such as smartwatch or smartphone. That was the basic idea. Giving a signal like a vibration or acoustic.
Thank you. Next question. Do you use actual construction accident reports to remove both human and equipment errors?
I don't understand. One more time, please.
In your research, do you use actual construction accident reports in order to remove both human and equipment errors?
Do you use actual construction accident report to remove both human and equipment errors? No, not in my research.
Okay. Next question. Have you considered fully automated house construction for affordable housing? Here in Canada, in big cities such as Toronto and Vancouver, the lack of affordable housing is a very big issue. Is there an opportunity for this technology for automated house construction?
I'm very positive to that. However, not in the near future. Not in the near future. In the construction area, and then for the construction robotics, compared to the manufacturing and industrial robotics or automotive industry, like autopilot technique, we are lag behind. We are very early stage. And then we have developed it, our industry and some key players in the construction robotics, we have developed several good prototype of the construction robot, but it is still, just to replace a portion of the construction worker's job. However, make a fully autonomous, it is too early to say that. Instead, maybe the prefabrication with more use of the industrial robotics, and then in the future, using the assembly robot on the construction site would be our next future. However, the fully autonomous construction work, well, it will not happen in near future.
Thank you.
Because of the uncertainties.
The next question, the commenter says, my impression is that the construction industry is quite conservative and traditional. Given that, how are these new technologies being accepted in the industry by both labor and management? An interesting question.
We need a lot of effort to change that pessimism. First of all, as the questioner mentioned, our construction industry is quite conservative. Even though we developed it a nice, a good, actually validated construction robotics, the construction company not just would like to use it because we do not know the return on investment. Because usually the construction robots, if we would like to use it, it will require at some point of the money at the beginning. However, the many construction firms simply does not like that because they already knew how they are going to make a profit from the construction process. So that's why we need a lot of research effort. We are developing the construction robot, but at the same time, at the management perspective, we need to develop how we are going to effectively evaluate the return on investment for the new robotics. And it's I would say it requires a little bit more time that we can get a valid framework to get it.
Second last question. We are nearing the end. The question is it challenging for the robot to detect a person if the safety vest is changed or removed, or if other countries use a different style vest?
That's totally possible. It's the same with a weather condition. How the deep neural network works is the training purpose is we are going to let the artificial intelligence know what would be the general features in detecting the human workers, for example, and it can apply to any other target object of interest. In the training data set, because most likely the most of the deep neural network that we are applying in the construction domain is still the supervised learning. And the supervised learning means we need the training images with the annotation. So question and answer, we need both of them. If we can include the different colors of the worker, as you saw before in my simulation video, all the construction workers vest has a different color, and that it was intended because I wanted to include a diversity in my data set. If the deep neural network is trained with such diverse data set, then the deep neural network tend to no longer consider the color value. If it is a best, it will take it as a best. Even though it is a yellow or even though it's a red, the deep neural network we identify it as a best.
Thank you. And the last question, in regards to the drone proximity detection, there is a limitation to the drone flight duration because of battery limitations. So the question is, has there been any thought to dealing with this problem to allow for monitoring over the entire construction day?
Amazing question. Using the drone fleet would be the answer. Only using the one drone. By the way, the drone's flight time is improving, and then our mechanical improvement was amazing. But anyway, still it is not enough to have a 24/7. So maybe the other idea is we use a multiple drone or drone fleet. So one drone monitor the side, and once it is close the battery out, then the other drone kickstart, and it's going to replace the previous one. So it's going to be a shift-based operation.
Thank you very much. I must say, as Sierra indicated in her opening remarks, I've been chairing Lunch and Learn for a number of years. We have never in the history of Lunch and Learn had so many questions. In fact, the number of questions almost equal the duration of your presentation. So again, thank you for all of the questions from our audience today. There was an amazing number of them. Before we close, I would like to thank Professor Daeho Kim for being with us today. Thank you for such an informative and entertaining presentation on human-robot collaboration in the construction industry. To everyone who joined us today, and I saw about 155 online, which is close to a record for a virtual presentation. We invite you to share your feedback on the School Lunch and Learn series. A link to our online survey is being made available in the chat at the bottom of the screen and will be shared with all of you who registered for this event after this event. Also, a link to the presentation will also be shared with all registered guests. And obviously there were some, because of time differences around the world, have chosen to watch it later rather than online. The School Lunch and Learn events are traditionally hosted on the second Wednesday of each month. So our next Lunch and Learn event will be in the new year on Wednesday, February 8th, featuring Professor Robert Irish. And the subject of his presentation will be ethics in an age of uncertainty. For more information about our next School and Lunch and Learn presentation, please visit the engineering website. We would also like to acknowledge and thank TD Insurance and Manulife, who are both sponsors of School Lunch and Learn through U of T's Pillar Sponsorship Program. If you're interested in learning more about School Lunch and Learn, please contact the alumni office at events@engineering.utoronto.ca. In closing, I would like to thank all of you for joining us today for today's presentation, and I hereby adjourn today's session of School Lunch and Learn. Thank you.